Bismillahirrahmanirrahim. I'm going to start about the nucleophilic reactions on aromatic rings, on benzenes. Previously, we have an idea that the benzenes undergo electrophilic substitution reactions. I've given you a very comprehensive lecture on that aspect. Let me review that very briefly before moving to my main topic of the day. We have an idea the benzenes do carry protons at each carbon. So whenever any electrophile approaches the benzene, a pi bond between carbon and carbon, it attacks at the electrophile. What happens is there is a new bond between carbon and electrophile. As this electron has been given away from here to the electrophile for the making of the new bond over here, consequently this carbon has to bear a positive charge. In order to neutralize that positive charge, a bond between hydrogen and a carbon is there. Then this electron is taken and is given to this carbon in order to regenerate in fact the double bond here between carbon and carbon. Consequently, what happens? Electrophile substitutes proton that is moved out from the benzene ring, and electrophile has been placed in place of the proton. So this is called electrophilic substitution reactions. This is the general reaction pattern of the aromatic compounds. Benzenes, they do react with an electrophiles. Similarly, in our last lecture, we used benzene, we performed nitration under electrophilic substitution reactions of benzenes. Then we performed the reduction and we generated, amines, something like that, aromatic amines and aniline in this very specific example. Then we use sodium nitrite along with HCl, keeping the temperature 0 to 5 degree. The reaction is called diazotization. A very comprehensive lecture has also been delivered on this topic: diazotization, diazonium salt formation, diazo-ion formation, diazonium as an electrophile. A mechanistic insight, a very comprehensive lecture has been delivered, which is available on YouTube. You may visit that for a precise mechanistic aspect of this reaction. Consequently, what happens? We generate diazonium salts. These are called the diazonium salts. In this nitrogen carries positive charge. So somebody having positive charge has the capacity to act as an electrophile. So such electrophiles, in our previous lecture as well, we use these diazonium salts as electrophiles and we reacted them with other aromatic compounds. Again, this is a benzene, so it is supposed to undergo electrophilic substitution reaction. As a result, an azo compound is produced, in this way. It is supposed to be the spectral product in this case. So this electrophile, which has been generated from diazotization process, starting from amines, this electrophile has been reacted with certain another benzenes, aromatic compounds, under the electrophilic substitution to get the azo-dyes, azo products, azo colorants, if you convert these organic compounds into respective salt, then it will become an azo-dye. Otherwise, it's an azo-colored. It's a separate uh, topic. Preparation of azo-dyes. It has also been very comprehensively discussed in one of the lectures. That is the preparation of an azo-dye, also available on YouTube. One can visit the link in order to get the proper insight into the preparation of dye, preparation of azo-dyes. So what I'm going to discuss today, that is the use of these diazonium salts for benzene's aromatic compounds to react with nucleophiles. I've told you in that lecture, we can produce diazonium salts through diazotization. Those diazonium salts could be used in more than one way. The one way is that they could be used as electrophiles, and they can substitute any of the proton on any other aromatic ring and undergoing electrophilic substitution. Similarly, another aspect of their reactivity, their reactions are that these diazonium salts could be used to make this aromatic compound react with the nucleophile, which is the topic of the day, how the aromatics or benzenes do react with nucleophiles. So I can write the topic just like this way. Nucleophilic reactions at aromatic rings. So I've given just a brief intro how the diazonium salts are produced, what are their main reaction patterns, means they do act as electrophiles. Let me give you a brief glimpse again into the diazotization. When we start with some sort of an amine, aromatic amine, we use sodium nitrate and HCl. We keep the temperature 0 to 5 degree, less than 5 degree. That is very much requirement. I've given you a very specific lab activity, related a lecture where aromatic amine, especially aniline, has been converted into respective diazonium salt. So where we used sodium nitrate and HCl, we kept the temperature 0 to 5 degree. What happened over there? So we received the diazonium salt having positive charge. As I've told you, this diazonium salt preparation, you need to keep the temperature 0 to 5 degree. If the temperature moves higher than 5 degree, then we have an idea these diazonium salts are unstable in nature. Diazonium salts are unstable, so that's why we need to keep the temperature less than 5 degree. As soon as the temperature raises 5 degree, there are chances that this nitrogen present in diazonium evolves in the form of nitrogen gas, leaving behind a sort of a positive ring, and we receive the nitrogen gas. The nitrogen gas evolves from the reaction mixture, leaving the benzene as a positive charge. In generally speaking, I will come to explain the exact mechanism how actually this reaction happens, whether positive is generated or not. Then what happens? At the same time, if any sort of nucleophiles are available, we have an idea the nucleophile can attack at the charges, so one can receive the benzene substituted with the nucleophiles, So these are the products which are generally not possible by the simple reactions of benzene. We have an idea that the hydroxyl groups are chloros, they are the negatively charged entities and they are supposed to be the nucleophiles. Under ordinary conditions, OH negative or Cl negative chlorohydroxyl groups, they cannot attack at benzenes because benzenes do carry the sort of a pi electrons, resonance of a pi electrons, so negative will repel each other. There won't be a sort of reactions under ordinary conditions. But here is the special condition. What has happened? We have generated an electrophile over here, somebody having positive charge. As soon as it gains energy with the rise of the temperature, the bond between this carbon and this nitrogen moves over here. As a consequence, this nitrogen moves out, leaving positive charge on the aromatic ring and then giving a place for the hydroxyls to attack and to give us a ring substituted with hydroxyl group. So mean the aromatic compound have undergone nucleophilic reactions, nucleophilic substitution reactions, one can say. These are only possible under very special condition, the diazotization creates diazonium salts, and those diazonium salts are supposed to act as electrophiles once the temperature is maintained around 5 degrees. If the temperature raises then the 5 degree, then those diazonium salts loses nitrogen, the evolution of nitrogen leaves the aromatic rings with a positive charge, then those will be possible to react with hydroxyl chlorobromo Cn negative cyanide. So some sort of nucleophiles if available in the reaction flask, they have the opportunity to react over here. So this is how the aromatic compounds do react with nucleophiles, giving us this sort of compound. These compounds are also important for the preparation of dyes. They are important for the dyes. As we have discussed in our previous lecture, that we generate diazonium salts, okay, and we bring in aromatic compounds having substituents with various nature. Those substituents could be the donating ones or they could be the withdrawing ones, depending upon the nature of the substituent. This diazonium either can attack at ortho or para, or if this body is some sort of a withdrawing, then this is supposed to act as meta. So this is why we need couplers with different substituents in order to produce different dyes, or even different shades of the same color, If we have a benzene having some sort of substituent which can donate electron to the ring, okay, it will facilitate the resonance of the electron, the pi bond conjugations, similarly. On the other hand, if we have some sort of groups which are withdrawing in nature, so they will withdraw the electron from the benzene, pull them out. Consequently, if an azo group is attached to that ring, there will be a movement of electron from the other ring to the other. So this is how this group present on the coupler the nature of the group present on the coupler can influence the resonant electrons in the system, in the conjugated system, especially in the azo-dyes, azo compounds. So they can give you different colors, they could produce different shades. So that's why we need to have a variety of colorant, a variety of couplers, you know. So how those couplers could be produced? One is the way that we could do electrophilic substitution reactions at benzenes, and we could generate a limited number of aromatic compounds with uh, substituents, you know, corresponding substituents. However, if we can bake the benzene to react with nucleophiles as well, then we have another dimension to produce another library of compounds having groups which are supposed to be sort of a nucleophiles in nature. So you can extend the library of aromatics. The number of aromatic couplers are increasing, so we have chances to prepare as many number of azo-dyes from the reaction of those couplers with the diazonium salt. So this is how the diazonium salt helps to produce the aromatic compounds substituted with nucleophiles. They could be used as couplers for the preparation of dyes, or simply they have their own special applications in organic synthesis in industry. So they could also be produced once we start from benzene, you know. Under ordinary condition, you can't produce phenol from benzene. You can't produce chlorobenzene starting from benzene, because the benzene is supposed to react with electrophiles only. So this is how they are supposed to be. These reactions. Now let me move into a bit mechanistic aspect, which explains it on a different direction, on a different mechanistic view. I will explain that to you as well, you know. The reactions of diazonium salts with nucleophiles, as it has happened over here, they are called Sandmeer reactions. Sandmeer reactions, very important reactions. They are known as Sandmeer reactions, you know. The reactions in which benzenes are made to react with aromatic compounds are made to react with nucleophiles. Those reactions in specific way are called Sandmeer reaction. So let me explain those a bit in details, so I can keep my topic as nucleophilic reactions are aromatic rings, or I may write it as Sandmeer reactions. You can write those as Sandmeer reactions, you know. On a brief way, I can write this way. Let's say you have some sort of a diazonium salt. We can simply react it with water, keeping temperature from 50 to 100 degree. As I have told you, we need to rise the temperature. We need to raise the temperature more than 5 degree. For better, it should be 50 to 100 degree. Then, as I've told you, this benzene ring will undergo nucleophilic substitution. You know, one nucleophile has been implanted, has been placed on the ring. So we will receive phenol. This will be the product. Or if you put in, let's say, cuprous chloride in the presence of HCl, yes, the temperature is again a bit higher, I think 50-60 degree. Sometime you need to raise a bit higher. We can write it 50 to 100 degree. Yes, we will have benzene substituted with chloride, chlorobenzene means the benzene has undergone a nucleophilic substitution. One of the proton through the diazonium salt formation has been removed and a chloro group has been implanted. So it's one of the very known reactions. Similarly, one can put in cuprous bromide using HBr under same reaction condition 100 degree. So we receive bromobenzenes, you know. Similarly, people could use CUF, HF 50 to 100 degree C, and we will receive, you know, the fluorobenzene. People have also used cuprous cyanide, CuCN, instead of HCN. People prefer to use KCN, not HCN. People prefer to use KCN. Same reaction conditions. What happens then? The benzene receives CN negative. Cyanide is there, so cyanobenzene is produced. Why the HCN is not used, KCN used? Because HCN is supposed to be a weaker acid. If it's a weaker acid, mean proton dissociation will be very minute. If the proton dissociation is a minute, then means CN negative generation will be low as well. CN negative will not be produced that much in the reaction flask. However, if we put in KCN, we have an idea. It's a sort of an ionic compound, K and CN. As soon as it is put into the flask, it will dissociate into CN negative and K positive. Now CN negative will be free to react, you know, to participate in the reaction. So that's why KCNs are preferred in place of HCN, because HCN is supposed to be a weak acid. You need to have free cyanide groups CN negatives, so that they can participate in that. So these reactions in general, few of the reactions available in the literature, they are called Sandomir reactions. What they are in fact, what is happening around in these reactions, the diazonium salt, the nitrogen removed from the diazonium salt, leaving behind the aromatic ring in the form of a cationic nature aromatic, which can further react with nucleophiles, chlorides, hydroxyls, bromides, cyanides to give the corresponding products, and those reactions are in combine are called Sandomir reaction, you know. So this is one of the aspect, one of the reactivity pattern of diazonium salt. You know, if we keep the temperature from 0 to 5 degree, then it will remain stable, and if we put in like any other aromatic compound, it can undergo electrophilic substitution. Electrophilic substitution, where this will act as an electrophile. This positive charge moves over here, and this nitrogen attacks at the carbon, one of the carbon of the benzene. So electrophilic substitution happens there, you know. However, in other case, if we allow the temperatures to rise, then, as I've just discussed, this nitrogen will evolve from here, leaving the nitrogen ring in cationic nature, which can react further with corresponding nucleophiles available in the flask, and the corresponding products could be generated, and those products, those reactions individually or in combination are regarded as Sandomir reactions. I will take one example and try to explain the real mechanism, that whether positive charge is generated on benzene or it takes the other way. Both things are considered. One can consider that the positive charge is generated over here because there is a, that is easy to understand, we have an idea that nitrogen carries positive charge and here is a bond between carbon and carbon. In order to balance this out, this is the electron of the nitrogen, it will not move, but this electron which belongs to the carbon is taken from here because the nitrogen is more electronegative, and then this electron also comes on the nitrogen. So as a consequence, the positive charge is balanced out and this nitrogen mean N2 evolves from here, from the flask. Now this carbon has lost its one of the electron, so it is supposed to be the positive entity. So when it gets positive, anybody around it which is negative has a chance to attack at this to give the corresponding product. It could be bromo, it could be fluoride, it could be cyanide, which can attack over at this positive charge carbon, or it can be a hydroxyl group that can come from the water, giving you the corresponding phenol. So this is how the diazonium salts are important. One way they can act as electrophiles, giving you the corresponding azo products, and they're important for the color chemistry students. The other way, those unstable salts could be used to make benzene react with the nucleophiles under the Sandmeyer reactions, and those become important for the students who are dealing with the electrophiles and nucleophilic reactions and the reactions of benzene. They're important for those as well. So I'm trying to convince both people at the moment. I'm trying to convince the students who are dealing with the reactions of benzenes, dealing with the basic reactions of the benzene. I'm trying to convey them that benzenes do not react only with the electrophiles, they do react with the nucleophiles as well, but under very specific conditions, which is one of the example is there. At the same time, I'm also dealing with the students of the dyes, color chemistry, to whom I'm trying to convey that the diazonium could go for electrophilic substitution, or they could also make the diazonium to react with some sort of the nucleophiles to receive these new aromatic compounds, and they could use them as coupler for the dye formation, because the compounds with having different substituents, they could behave differently while acting as a directing group for the diazonium ions when they come for the electrophilic substitutions on these benzenes, So let me give you a glimpse into another aspect of the mechanism for the Sandmeyer reactions, what really happens. Let's say we can take one example, how few people explain these reactions as well. Diazonium salt, let's say we are putting cuprous chloride in the presence of HCl. The reaction temperature is 550 to 100 degree. Okay, what happens then? This chloride, in fact, which is available in the form of a diazonium salt, is attracted by this cuprous chloride. The cuprous, we have an idea this bed is a metal. It can attract electrons. It needs electrons. Metal is electron deficient, and it's a Cu+1 at the moment. Cuprous, it can be cupric, so it can have both states. So that's why it will attract towards it. So the things look like, nothing change over here, but we will get something like that. We get something like that. cuprous chloride has been formed during when the reaction has been raises over here, then what happens, in fact, this cuprous chloride, it undergoes a homolytic bond breakage. A bond between copper and chloride is broken as homolytic fission, homolytic cleavage, giving us CuCl radical. One radical will be generated and we will have a Cl negative, something like that, Then what happens actually, this cuprous chloride, which carries one radical, which is a radical and carries a single electron, unshared electron, it will give away to this nitrogen, which is an electron deficient in diazonium salt. What happens, in fact, so nitrogen has positive charge over here. Here is CuCl. It gives this electron to this one. It's a pretty common when any radical attacks on any other entity, it accelerates the homolytic cleavage of the bonds there. So once it gets electron from here, so what happens, we do expect the nitrogen becomes neutral. The positive charge has been balanced by this acceptance of one of the electron from the copper. Then what will happen over here? As I've told you, the attack of the radical generates other radicals. What happens? The bond between carbon and nitrogen is there. It also undergoes homolytic cleavage from here as well. It is supposed to undergo. As soon as it goes over there, one of the electron moves from copper to here, it undergoes a cleavage there as well. So what happens? The nitrogen receives its own electron from the bond, and then in the form of a neutral entity to moves out as nitrogen. And two, what happens over here, this carbon of the benzene, it carries one of the electron which is its own, the carbon's own electron is present in the form of a radical there. So this will evolve as N2 nitrogen, leaving phenyl radical in the flask. We have an idea of one of the radical generated from Cl having one unshared electron available will come over here to react with this radical. So reaction between these two radicals will generate the product which is the chlorobenzene. In fact, this is how the final product is received, where benzene has undergone a nucleophilic substitution. Why nucleophilic? Because one of the nucleophile, somebody having nucleophilic nature, has been implanted on benzenes. So this is how the Sandman reaction proceeds, This is the one way where benzene is supposed to become a phenyl radical before the formation of final product. The other way was where we consider that the phenyl ring becomes a positive cation, then it is attacked by the surrounding some sort of a nucleophile present in the flask, like water is there, then hydroxyl can attack, or chloride can attack, or cyanide can attack. So this is one of way where the reaction mechanism is supposed to proceed through the radical formation. The other way was, which I've already explained to you. Okay, if we have started over here with bromide, so we will have a bromides over here, and finally it will have a bromide over here. So if we have proceeded with cyanide, the same way you can replace the chlorides with cyanides, and simply your product would have carried the cyano group. So all Sandmeyer reactions could be explained through the same mechanism, one mechanism which is really supposed to be uh, based on a radical formation, and the other was where I told you the nitrogen evolves leaving phenyl in the form of a positive charged entity, which subsequently reacts with surrounding nucleophiles and gives corresponding products. So this is why I am trying to convey you guys that the diazonium salts important in two ways. Once they could be used as electrophiles for the preparation of azo compounds, where the as diazonium salt, diazonium ions are supposed to act as electrophiles. However, the other way is that if you prepare the diazonium ion, diazonium salts and raise the temperature over 5 degree, then they decompose, the nitrogen evolves, and the remaining aromatic part, aromatic ring, could undergo nucleophilic substitutions, and you could receive the uh, corresponding aromatic compounds having nucleophiles. So they can increase your library of the compounds, and those could be used for the preparation of a number of colorants, a number of dye molecules, number of azo-dyes. As we have told you, the presence of the substitute at the benzene is very much important. If it is a donating or it's a withdrawing group, it can enhance or reduce the resonance of the conjugated electrons within the systems, and that can really influence the color generations or the shade formation of in the aromatic compounds in azo-dyes. So thank you very much for your attention and kind time. Please, if you have any questions, if you have any confusion in your mind, you may ask me. You may approach me via WhatsApp, or you simply could put up your question in comment area. I will be happy to respond at my earliest convenience. Thank you very much. Assalamu alaikum.